Start with course number 3. Today we're going to talk about the TF transformation system. It's where you handle all the reference frames, which is an important aspect of mobile robots. And then I'm going to talk about the user interface, the RQt user interface, which is tools that are available for you to analyze and process things in ROS. And then we're going to talk about robot models, which are a description of your robot. Now you're working with the Husky robot, but many robots exist in this format. And then, just as a background knowledge, we're going to quickly introduce the simulation description format, the one that you loaded when you were loading in Gazebo these different worlds. So first, for the TF transformation system. It's a system to keep track of all the coordinate systems that run your robot. And here's an example. On the PR2 robot, you see that it has many coordinate systems. So essentially the base, there might be a map coordinate system, and then each joint, each sensor has its own coordinate system. And with TF, this allows you to ask questions like, what is my base currently in the map coordinate frame? Where is my hand relative to my laser sensor? And it also allows you to do these spatial, but also temporal questions like, where was my hand compared to my base 5 seconds ago? So how it does that, TF, it maintains internally a tree, a temporal tree, between the relationship between coordinate systems. Essentially, it's an entire, like a tree of coordinate systems which each have a transformation in between. Additionally, TF allows you to then transform points and vectors and other coordinate systems between each other. And internally, it's implemented as a publisher and subscriber model that you already know on 2 topics, the /TF, where all the moving coordinate systems are published and subscribed on, and the TF static. Those are the ones which are static on one rigid body. If you have 2 coordinate systems and they don't move, it's stored as a static for performance reasons. So the TF is a little bit of a different subscriber publisher model, since multiple nodes publish on the same topic and subscribe on it. When you work with TF, you're going to load a TF buffer, which subscribes to the /TF and TF static topic, and internally buffers all the information such that you can do math with it. So you query the transformation that you want from this buffer tree. On the TF topic, and this is just background information, is essentially an array of transforms which internally have a header, timestamp, a frame ID, which is the source frame ID, and they target the child frame ID. And then internally it tells you, okay, the transform consists of this translation and this rotation. On the right-hand side, you see an image how this typically looks. You would have a base link and head frame, and then in between you have these transformations. There are several tools that facilitate working with TF. One is the command line tool, where you say run TF monitor, which spits you out all the current transform tree. And if you need specific transformation between 2 transformations, between 2 frames, you can do run TF echo, and then the source frame and then the target frame. Often, once a tree becomes very complex, it's convenient to print an image like that, and you can do that with this tool, run TF view frames. It listens for 5 seconds on the TF topic and then does a nice PDF of the current transformation tree. And the most important is the TF plugin in RViz, where you can visualize these coordinate systems. To do that, you click on the bottom left on add and add TF. Make sure again here that your fixed frame is reasonable, a frame that exists. And then here you would see it would show you, and you can have several settings, it would show you the transformation tree in 3D. It's a very convenient tool to look if everything is correct with your transformations. Now if you want to create a transform listener, so if you want to request transformations in C++, what you would do is to create a TF buffer, which internally stores all the trees over time. I mean, what you need is a TF listener, which actually subscribes to the TF and TF static topic. So, and you hand it in the constructor for the TF listener, you hand in the buffer, such that the TF listener knows to fill in this buffer, okay? And again, make sure that this listener is a member of your class, such that it doesn't run out of scope and is able to do the work in the background and listening to the TF topics for you. Otherwise, if you lose the TF listener and keep the TF buffer, the TF buffer will not be filled, and you'll get an error when trying to do transformations. Now, to look at transformations, you would use the command lookup transform on the TF buffer. The TF buffer has these commands to also wait for a transform or look up a transform or check if it exists, etc. And then you would say here, lookup transform first the target frame, then the source frame from where to where do I want to transform, and then the time at which I want it. Now, if you do time now, and we'll talk about ROS time in the next lecture, then it might be that the TF buffer has not yet filled up to that latest time. So to get the latest transformation, you would do, for this time parameter, you would set in ROS time 0, which tells the TF buffer, get me the last transformation that exists in the buffer. Here's an example. It's a simple main file. You have the node handle. You would, like it said, you create the TF buffer and the TF listener, and you hand in the TF buffer to the constructor of the TF listener. Very similar to previous examples, we go into a loop with 10 Hertz, and then here you see now a try and catch scope. If in case this lookup fails, it throws an exception. So if it's not around, or if it's too early in the beginning, so this exception is caught. Instead of your program crashing, the exception is caught, and the user is warned, saying, okay, I couldn't look up this transformation. Then it sleeps, and if it's able to look it up, the transformation, it's stored in this transform stamped, and then you can do math with it and do whatever you want with this transform. So I think the important thing is here to use this try and catch, because sometimes the TF can fail if things are not ready yet, and you don't want your program to crash. So with this try and catch, you can catch this exception and make sure it's safe for the user to use. Now, talking about the RQt user interface, it's a ROS adaptation of the Qt, standard Qt interface, and allows you to set up custom interfaces. There are many, many existing plugins, and we're going to talk about some of those, and you can also write your own. And then if you have kind of like a robot that you want to control, it's very simple. You can drag and drop together a commander user interface like shown here on the right-hand side. You can run RQt with ROS run RQt GUI, or just simply RQt in the console. Then on the top, you have a menu where you can add all these plugins that we talk about. So here's a few plugins that are convenient tools when working with ROS. First one is RQt Image View, which when we do ROS topic echo on an image, that would just get you a bunch of numbers which you can visualize in your head as an image. So here with this tool, you can subscribe to an image, and it visualizes, for example, a camera image as image, and you can check what is running on my cameras, etc. This is another tool that we pre-installed on your system. It's a convenient tool to plot 2D information over time. You can have multiple plots in one, you can have multiple lines. It's similar to the MATLAB plotting tool. Make sure to check out the commands on top where you can pause, play, reset, change the colors, etc. And you can run it with ROS run RQt multiplot. This is going to be part of your exercise to plot something with this tool. So you can run it with ROS run RQt multiplot, and then play around a little bit. It's a GUI, so it's easy to discover the functionality of it. RQt Graph is a nice tool. It visualizes the current state of your ROS system. So it shows you the running nodes and the topics and how they're interconnected. And then again on the top you can show, if you want to visualize nodes, topics, dead things, etc. And if you have like, okay, my node is not running, why doesn't it receive any messages? You can either work in the console by checking the node and the subscriber information, or open Arcute Graph, and you would see that these two nodes are not connected. Somewhere you misspelled maybe a topic name. The Arcute console is another tool where if you have multiple consoles open and they spit out messages, it's hard for you to check every console, right? Especially if you have a robot without a screen. So Arcute console gathers all this information and put this information in one user interface, where you can also sort in about the severity level if you want to only see warnings, errors, etc. And you can launch it with ROS Run Arcute console. Another good tool is the Arcute logger level tool, where we saw when we use this ROS logging, where we have ROS info, ROS warning, ROS error, ROS fatal, etc. Each node goes into ROS info severity level. With this GUI, you can very conveniently change this. So if there's a node which spit out too much information, you say, okay, I'm going to put this, I only want to see the warnings in my console. So you select your node and tell it to put the logger on warning. Or if you have a tool that misbehaves and you want to check the inner details, typically the ROS debug information is not shown, but here you can set it to debug mode and get the debug information if you want to analyze the behavior of the node. Okay, so for the last part, I want to talk about robot models. You already worked with the Husky robot model, and this is a little bit background information of how these robot models are built up and how you could, in the future, create your own robot models. Robot models are defined as XML format description of your robot. Internally, it consists of a kinematic and dynamic description. We will see an example in a second. It also contains a visual representation. Here it is kind of like a mesh of your robot. And it contains the collision model, which is important for Gazebo to know where do I check for collision, how does the robot interact with the environment. Often you would use kind of like a nice high resolution mesh model for visualization because it's nice to look at and represents the reality better. For collision, it's often nice to use primitives because a mesh can be arbitrarily complex to check for collision and would take a lot of time in Gazebo. So people prefer a nice mesh for visualizations and then primitives such as boxes, cylinders, etc. for collision. And then URDFs can be, if you have a complicated robot with options, do I want a sensor or not, etc., can be complex. So there exists the script language Xacro to allow you to modularly build your URDF. It's not something you're going to do, but if you see one day that Xacro is used, this is used to generate robot models in the URDF format. Now, in the URDF format, a robot consists of a set of links and joints, and the joints hold together the links. In this case, you would have a robot, let's say here, the short arm and the longer arm, and the joints would be in between the rigid links. In the URDF, then typically you would have the name of the robot and then a link of links on top. These are all my elements of the robots, and then down there, a list of joints. How are they interconnected? Here's an example for a link called link name. And then you have the visual tag, which tells it the geometry. I want this mesh collada file to be shown. For collision, it could use the same mesh, but here in the example, it uses a cylinder with length 0.6 meters and radius 0.2. And then for dynamics, it's important to specify the mass and the inertia of this link. Here with 10 kilos and 0.4 and 0, so the entire inertia matrix would be stored here. And then in the joint, you tell it, okay, this is the name, let's say knee, an arm joint, here's the joint name, and it's of type revolute. There's also prismatic joint, spherical joint, etc. And then you give it information about the rotation axis, the limits on the effort, essentially the torque or the force. You give the limits about position, and then you tell it, okay, the parent link is this one, and the child link is the following. then these robot description in ROS, these URDFs, are stored as a string on the parameter server. So any tool like Gazebo or Arvis that uses this robot description format can load it from /robot description. And then you can visualize the robot model in Arvis with the robot model plugin, and you're going to do this in the exercise. And then check the settings that you make sure that the robot model plugin subscribes or is set to the robot description parameter, okay? And then if you were wondering how the Husky already loaded for you in Gazebo, just for you to understand where it came from, when you loaded Husky empty world, internally you see that somewhere it included from the Husky Gazebo packages spawn Husky. And spawn Husky you see down here printed has different options. And here you see it loads the parameter with name robot description, and it executes this xacro script and tells it where to find the Husky description. This way, the robot description was generated through xacro and loaded on your parameter server. So if you want, you could do ROS param get /robot description, and then you would see the entire generated URDF. It's not, if you do ROS param get, it's not very human readable, but essentially you get the entire robot description on the parameter server. Now, very similarly to the robot description format, Gazebo works with a simulation description format. It's essentially an extension of it because it can hold, the SDF can hold robots, but it also contains information about the environment, such as light, gravity, and also other objects like here the house or the car. And also can model sensors that you use, laser sensors, camera sensors, etc. Plus, of course, like the URDF, it contains the robot. SDF came originally from Gazebo, and URDF is used in ROS. Conveniently, Gazebo internally converts your URDF to use it automatically to an SDF. So if you have a robot, you can work with URDF. And then if you want to work with environments, create your own environments, and typically you would work with SDFs. So it's just that you know the difference between these two formats. This is it for this lecture. Okay, so we'll have Dominic talk you through exercise 3.
Okay, so exercise 3. The main goal here actually is that you now for the first time write the publisher, and we're going to use that publisher to also for the first time close the entire control loop. So before you had that tele-op twist keyboard node commanding twists to the robot. But actually what you would normally want is that you get somehow a sensor input, and from that sensor input you generate a command to your robot. So then closing the control loop. And that's what we're going to do today. Since yesterday you've been working on the laser scan, which is in our case the sensor input. And from that now we are then going to generate an actual command to the robot. The world that we are going to use for this is here on our homepage. There's a zip file with ROS worlds. There's one inside with a single pillar, just actually an empty world with just one pillar, and there's one with 2 pillars. So take the world with 1 pillar, because you're gonna need that, and you can store this in your package. In a folder called worlds, and then you can put this world that you find in the zip file here. So that's the first point. Then number 2, so you need to rewrite your callback such that you can extract the position of this pillar from the laser scan. What you did yesterday is just finding the closest point in the laser scan. And since the world is empty and only has 1 pillar inside, the closest point will be the point where the pillar is. And further down there's these 2 images. So the one on the left, I've already shown this to some of the people yesterday, is how, so this part here is how the laser scanner looks from the top. The gray area is the field of view that it has, so it's not 360 degrees, there's a blind spot at the back. And this angle here is the minimum angle that it can do, and there's a maximum angle where the line to the front is 0. Okay, and then there are these individual rays in the laser scanner that have an angle increment with respect to the previous angle. So then if you, let's say, calculate angle mean plus 2 times the angle increment, you'll get the angle of the second ray. And the ranges array that you used yesterday is then constructed the same way, that it has the size of the ranges array is the number of rays that you have. So ray number 2 is number 2 in this ranges array. Okay, so with this angle plus the range, you can then calculate the XY position of the pillar. Simple sine and cosine operation. And this here is the coordinate system of Husky. The forward direction is X, sideways is Y, and up is Z. From this extracted position, you then should generate a command velocity to Husky. So there's this topic / command vel that you can send a twist. So write the publisher in your node that publishes a command velocity to Husky. The way you fill this command velocity is that you put in a constant linear x velocity, so such that it just drives forward, and then you control the angle of the robot such that the pillar is in front of you. So the goal is actually to drive towards the pillar. Okay, so you should control the angle to 0. You do this by setting an angular velocity on Z, such that Husky starts to turn around. Okay, so you can write a simple P controller where you put the desired angle, which is 0, minus the current angle that you've extracted from your laser scan times the P gain. And then Husky should slowly turn towards the pillar while driving forward. And all of this you have to write in the callback of the laser scan function. The way that ROS works is that a lot of it is callback based. So the sensor generates a sensor message. That sensor message is sent out to, in our case, Husky high level controller, triggers a callback. That callback works with that laser message such that it can compute the command. The command is then sent out to Husky, and the callback on Husky is receiving this. So you see that there's a callback chain going on. And then the last parts are adding the robot model to Arvis, I'll show that later, and adding the TF display to Arvis. The last step then is that you have to write another publisher. So you wrote the publisher for the twist, but you can now also write the publisher for visualization markers for Arvis. This is useful that you can visualize stuff in Arvis that you did. So in our case, this is the position of the pillar that you've extracted. You can visualize this in Arvis using a sphere marker or a cube marker. And you'll find some information here on this link. So these are all the possible markers that exist. And you should just put a marker where you think that, or where you extracted the position of the pillar. Now there's also quite some stuff on how to write this. So we have here an example of how the publisher has to look like for such a visualization message, and also the implementation. So all the parameters that you can set, like scale is the size. There's one important thing is color. There's an alpha value, and if you don't set this to 1, it will be invisible, and the default value is 0. and 0 is invisible. So put this to 1, and then you'll actually see the marker. Another important thing is here, Peter has talked about the TF frames. Now, the marker also has a frame. The position that you're going to extract of the pillar will be in the frame of the laser scanner, right? So the laser scanner measures everything with respect to itself. The distances is with respect to the laser scanner and also the angles. So the position that you're going to have is also in the frame of the laser scanner. Now, to display the visualization marker correctly in ARVIS, you have to put here the frame of the laser scanner. Because then what ARVIS does is it takes in this message, sees, well, this is in the frame of the laser scanner, but my ARVIS is in the frame of ODOM. So to visualize it correctly, ARVIS will then automatically transform this from the laser scanner frame to the ODOM frame using TFs. But that's all in the background, and you don't have to do anything for that. Yeah. That's the easy way to do it. Then there's a hard way. The hard way is that you don't specify the laser scanner frame in the message, but you transform the point by yourself into the ODOM frame and then send the point in the visualization message as a point in the ODOM frame. But for this, you have to have access to the TFs, and you get that by writing a TF listener. So then this is how the world looks like. There's a single pillar, and Husky should actually drive towards it. Now I'll quickly show this. So in Gazebo, you have to zoom out quite a bit to actually see the pillar. So it's placed a little bit too far away. Now down here, I paused the simulation to zoom out. Now I can let it resume, and you see that Husky is now slowly driving towards it. I'll pause it again and switch to ARVIS. Now this is still the old ARVIS setup that we had. So you see the laser scan, and also here the points of where the laser hits the pillar. Now what we can do here is we can add now the TFs. Okay, and then we'll get here all the transformation that are existing for Husky, such as the wheel, the base, the laser scanner, all of that. And we can also add the robot model. And then Husky is here nicely visualized. And I've also prepared the marker. So by topic, Husky high-level controller, I called it visualization marker, and I can add this here. And so I quickly had to let it run such that it sees that it first subscribes or gets a message, and then you can see here the green sphere is my marker, where the algorithm has extracted the position of the pillar. And now I can let it run. So you can see there Husky moving towards the point, and then in Gazebo it will eventually drive into it. Yeah. Now it can't really. No. Now it's lost. Good. So, and then nice to see here now is that if if you can't really detect anything anymore, you now really see what the visualization marker can do for you. So it's a great tool to actually debug stuff. Now you see that the point that I extract is jumping around. So something is clearly wrong. Right? By the way, I put some output to the terminal that extracts the position of the actual, or where he thinks that the pillar is, with X and Y coordinates, but you don't have to do that. That was just for me for debugging purposes. Evaluation checkpoints are first that Husky should actually drive towards the pillar. So you get some points if Husky just drives by itself somewhere. And if it successfully hits the pillar, you get some more points. Then an important thing is that the RVIS configuration show. So you should be able to show TFs, the robot model, and the laser scan together with, this is missing, oh no, and then together with the visualization marker, but this is evaluated separately because it's a little bit more work than the three things above.